Certo. So, shall start. First talk of our session is by João Nuno Mestre from University of Coimbra, and he'll talk about the formations of Lie group points.
Thank you, Bruno, and thanks a lot for the invitation. It's nice to talk here. I'm always happy to talk about this. It's a topic I like a lot. So I will tell you a little bit today about Lie groupoids and their deformation theory, or deformations of Lie groupoids and how to study them. And I'm going to not assume that people do know about Lie groupoids very well. So if you all know and feel very bored, you can tell me later and I can skip ahead some stuff, but I'm assuming that it's good to introduce these things. So this is more or less the plan of the talk. I will first give a brief introduction to Lie groupoids and then talk about their deformations and cohomology and how do they relate to other structures so that we can get some rigidity results both for Lie groupoids and for the structures they relate to. I'll focus particularly on foliations. And in the end, I just want to give, I'm trying to give in this talk a glimpse of this theory. So I also want to leave some open problems, both related to deformations and just to Lie groupoids in general. So to start with, I would like to just give a panoramic view of the history. Of course, this is very skewed by the person telling the history. So it's based on what I felt were important things. So Lie groupoids were introduced by Eresman in '58. And at the time they were used to help in the geometric study of PDEs, for example, but also for different things. And there were a lot of different mathematicians like Cartan, Grothendieck, Spencer, Compere, Pradines, and Molyneux who came and used techniques directly involving groupoids or related objects like Lie pseudogroups or something like that. But in the 70s, groupoids came to be a bit more prominent in the study of foliations, mainly through the work of Häfliger, who started using groupoids to describe holonomy. Later on in the 80s, they were very useful in non-commutative geometry as well, building some C-star algebras out of Lie groupoids. And namely, Kohn used them to give a proof of the Atiyah-Singer index theorem. Now, closer to my own specialty, in the 90s, Weinstein introduced, not only him, but he was one of the champions of using groupoids to study Poisson geometry, and many new applications started showing up. So in the 2000s, coming from all this background, there was an explosion of new results on the theory of Lie groupoids themselves as objects in their own right. So just to give you an idea of some of the themes, there was now a well-formed Lie theory for Lie groupoids so that we could differentiate and integrate, just like for Lie groups and Lie algebras, not only the Lie groupoids themselves, but their representations and lots of associated objects to them. So there was a well-described representation theory for Lie groupoids now, also cohomology theories for Lie groupoids, and there were many new applications to many aspects. Here, just to mention a few, Poisson and Dirac geometry were some of the ones I know better, perhaps, but also in the fields of geometric mechanics and PDEs studied through geometry, and also the study of some singular spaces like differentiable stacks. Lie groupoids proved useful for all of these. But now, what are they? What is a Lie groupoid? So the first definition doesn't tell me much, honestly, but maybe it tells some of you something. So a groupoid is just a category with all arrows invertible, with mainly a small category. So we have sets of objects and sets of arrows. But and then a Lie groupoid is a groupoid which is also smooth, just like a Lie group is a group which is also smooth. It's also manifold. But to me, to understand what this actually means, I need to break it into pieces. So how do I do that? A Lie groupoid will consist of two manifolds, one codifying the arrows of my groupoid and one codifying the objects of my groupoid. Each arrow starts and terminates, or as a source and a target, at two objects, which may or may not be the same one. And I'm going to ask that the source and target define submersions from the space or the manifold of arrows that I denote G to the manifold of objects, which I'm denoting M. And I want to be able to compose arrows, but I can only compose arrows if one of them starts where the other one ends. So I'm going to have a partially defined multiplication on this submanifold of pairs of composable arrows, which are given by an arrow starting where the other arrow terminates. And whenever I have two arrows like that, I can form the multiplication. There's going to be a unit for that multiplication. So for each object, I have a unit, this defining and embedding U from the space of objects or the manifold of objects into the manifold of arrows. And I also wanted every arrow is invertible. So I have an inverse diffeomorphism from the manifold of arrows to itself. And then, of course, I need to ask some axioms, but you can guess what those are, perhaps, or you could work them out if you needed to. We're not going to need them. They're going to be the axioms making these into the structure maps of a category. But you could...
Só um minuto.
Yes,
Eu acho que congelou a sua tela do slide, que está vendo primeiro ainda.
Oh, that's bad.
Yes.
Okay, let me see if... should I stop sharing and start again, maybe?
I guess.
Okay. What do you see now?
Now outline.
Okay, so the outline I mentioned, it's not too important. The history, I guess it's just something I said out loud and you probably can skip. Is it changing the slides as I change?
Yes.
Okay, great. So now here is the important part, the definition of what a Lie groupoid is. The pieces are, and please do let me know if it happens again. I hope it doesn't, but just let me know. So for a Lie groupoid, we'll have, as I mentioned, a manifold composed of all arrows of my groupoid, a manifold composed of all objects. For each arrow, I will have a source and a target, these defining submersions from arrows to objects. I'll have a partially defined multiplication. I have units and inverses, and they behave nicely. For example, the multiplication is associative. The inverses and units behave with respect to multiplication as you expect. But I think probably the best way to understand what they could be is by examples. So as I heard from Enrique Burstein last week, the definition is as good as 3 examples. So I'll try to give you like 6, and hopefully that redundancy will save the day. So the first example would be of a Lie group, and hence the name Lie groupoid as a generalization. If you think of a Lie groupoid such that we only have one object and arrows from the object to itself, so that we can always compose any 2 pairs of arrows, any pair of arrows, that's the same information as a Lie group. And one thing that we can notice is that Lie groups are useful in particular because they integrate Lie algebras, or we can think of the Lie theory as putting Lie groups in correspondence with Lie algebras. A second example would be if we just have any smooth manifold M, we can consider the manifold M times M and treat it as arrows, because they're pairs of points on M, and an arrow XY, this pair XY, will have a source, which is the point Y, and the target, which is the point X. So we think of XY, this pair, as an arrow, and so we can multiply the arrow XY by the arrow YZ and obtain the arrow XZ. It's a groupoid such that for any 2 objects, we have one and only one arrow between them. And note that, again, we have some Lie theory around here, because there's this infinite dimensional group that, in a sense, integrates this infinite dimensional Lie algebra. The group of diffeomorphisms of M integrates the Lie algebra of vector fields of M. And one way we can describe the diffeomorphisms of M are as functions from M to the pair of M, so the space of objects to the space of arrows of this pair groupoid, such that they are sections of one of the projections. And if we compose with the other projection, we obtain a diffeomorphism. So for this, just like for the Lie group, we have an integration of a certain infinitesimal object, which is the Lie algebra. For this pair groupoid, there's an object associated with that integrates an infinite dimensional Lie algebra. And this is going to be a general phenomenon. Most Lie groupoids, or any Lie groupoid, has an associated group, which is infinite dimensional in general, which is given by sections of the source map, which composed by the target map to a diffeomorphism. And it's always going to integrate a certain infinite dimensional Lie algebra of geometric type by which I mean that those Lie algebras are going to be Lie algebras of sections of certain vector bundles. So this is one of the ways Lie groupoids show up in geometry, is as finite dimensional objects that serve as codifying some sort of integrations of infinite dimensional Lie algebras. So bringing it down to the world of finite dimensional geometry. But I didn't give you enough examples yet. So some more interesting examples could be, if we want to study a submersion, we can codify it in terms of the following groupoid. We take as objects of my groupoid just the points of the domain of the submersion. So the submersion goes from M to B. And I take as objects the points of M, and as arrows, pairs of points in M, just like for the pair groupoid, but now I only take them if they are in the same fiber of the submersion. And the rest of the structure is just like for the pair groupoid. So in particular, if it was a submersion onto a point, I would just recover the pair groupoid. But I also could just take what's called a unit groupoid, which is when I have the submersion being the identity. And in that case, the only arrows I would have are identity arrows over each object. So it's a way to codify just simple differentiable manifolds as Lie groupoids. So we've seen how to codify manifolds, Lie groups, and submersions. Further, we can codify a vector bundle as a Lie groupoid. It can be seen, it's essentially as a bundle of Lie groups, of abelian Lie groups, which are the fibers with the addition, right? Because we can take the source and the target of any vector of my vector bundle, thinking of the vectors as the arrows. The source and the target are both going to be the projection, which is a point of the base, which is going to be the manifold of objects. And then the multiplication between composable arrows, two arrows are composable if and only if they're in the same fiber, and the multiplication, the groupoid multiplication will just be the fiber-wise addition. Yet another groupoid that I can always form out of a Lie groupoid is what's called a tangent groupoid. So if I apply the tangent functor to a Lie groupoid, I will obtain the tangent bundle of the Lie groupoid as a manifold of arrows for over the tangent bundle of the base as manifold of objects. So I apply T, the tangent functor, to both the space of arrows, the space of objects, and all the structure maps, and I obtain a new Lie groupoid, essentially just by functoriality of the tangent functor. That's what makes all the structure maps behave like maps for a groupoid. And I'm mentioning this example because it will be very important in the study of deformations. So we will use this one again. I will just check the chat. Oh. Now, a little bit more intricate is the example of an action groupoid. So we can also encode actions of any Lie groupoid, actions of any Lie group acting smoothly on a differentiable manifold. We can form an arrow, a groupoid for which the arrows are pairs of an element of the group and the point of the manifold. And that arrow would go from its source, which is just the point, to the target, which is the element of the group acting on the point. So it's a way to label G, an element of my group, going from X to GX. That's going to be an arrow, which is the pair G, X. And the way the structure maps work is just by using the multiplication of the group. And it will nicely codify my action. We'll see a little bit later exactly how. But now, perhaps the example I want to talk a bit more today is that of foliations, because we'll see them when we look at the formations. And I want to somehow think of how can I get arrows out of a deformation? Sorry, not out of a deformation, out of a foliation. So what are foliations? Foliations are partitions of a manifold into submanifolds, which locally fit like a product. And they have these infinitesimal counterparts of distributions which are involutive. So involutive subbundles of the tangent bundle. Here are some pictures of foliations. I imagine you probably all have seen Kronecker foliations on the torus, but if not, the torus can be foliated by lines. And these lines, if I take them to have a rational slope with respect to, let's say, this side of one of the circles of the torus, one of the factors, then they will loop back to a circle looping around the torus. And so I imagine that I'm foliating, so I'm taking parallel lines to this line, and that will give me a foliation of the torus by circles that spiral around the torus. But if I just tilt just a little bit to get an irrational slope on the lines, then what I would get is that each of these lines, as it loops around and around the torus, never closes back, and it's actually going to be dense in the torus. So here we see already that for foliations, I didn't tell you what the deformation is yet, but if I think of a deformation as changing a little bit my structure, if I just tilt very, very little, infinitesimally little, my foliation by circles, by changing a little bit the angle, I can get the foliation by dense lines. These two have very different behaviors, so we see that it's not a very stable, not a very rigid condition, this foliation. Now, to encode foliations via groupoids, we are going to use the notion of holonomy. Holonomy is kind of a measure of the dynamical properties of a foliation. It measures how much the leaves, so the submanifolds that define the partition, I'm going to call them leaves. And the holonomy measures how much the leaves wrap around each other. The way it's defined is the following. I want to define the holonomy along a path, gamma, that lives completely inside of a certain leaf. Let's imagine that gamma is here in this central leaf, and there's all these other black leaves around. The way holonomy works is the following. We take transversals along, well, first of all, there's charts in which my foliation looks just like a product of RNs with Rn, Rk minus Ns. So in this case, the plane looks just like a product of vertical lines with horizontal lines here. And inside of those, I can take a transversal to my path gamma at the beginning of the path, so at X, which is the starting point of the path, and the transversal a bit further, such that the transversal is also in a foliated chart next to the first one, and then another transversal in the intersection of the second and the third foliated chart, etc., until I have transversals joining the intersections of each two consecutive foliated charts. Then I can follow along from this transversal to the next by getting the intersection with the leaves. So if I start, let's say here at the intersection of the transversal with one leaf, there's only one way I can get to the next transversal inside of this chart, and then I'm in the second chart. There's only one way I can follow to the next transversal inside of the second chart. Now I'm in the third chart, and I keep going until I have a transformation from the transversal at X to the transversal at the endpoint, Y. So this is going to define a diffeomorphism of the transversal at X to this foliation onto the transversal at Y of this foliation. Of course, this is not completely well defined because I chose transversals, but if I, pardon, if I choose to instead work with germs of diffeomorphisms, this will be well defined on a germ of transversal around X and the germ of transversal around Y. So for each path inside of a leaf, I get a holonomy transformation between germs of transversals, okay? And just to get a very simple example here, if I think of the Mobius band foliated by circles in which I have a central circle and all the other ones are double covers of it, let's take a loop in the central leaf and see what is the holonomy of this loop. Well, it will take here my point on a transversal, which is the circle, and as you can expect, if you've touched a Mobius band before, it flips around my transversal. So the holonomy will generate a group which is Z2 of transformations at my transversal. And so I'm going to tell you two groupoids that we can get out of a foliation. The first one is perhaps a bit simpler to describe. If I start with the foliation F on M, I'm going to take the objects of the monodromy groupoid, also called fundamental groupoid, by one of the foliation. The objects are just going to be the points of the manifold, of the ambient manifold. And I'm going to have arrows only between points which are in the same leaf. And arrows will be leaf-wise homotopic classes of paths such that the path is completely inside the leaf, and the homotopy classes are only with respect to homotopies that stay inside the leaf. And then I can compose such homotopy classes of paths just by the class of the concatenation. Okay? And very similarly, I could take the holonomy groupoid, in which again I take the objects to be points of my manifold, and the arrows, instead of being homotopy classes, they will be holonomy classes of paths inside the leaf. So I'm going to consider two paths equivalent if they induce the same holonomy transformation. And again, I take the composition to be the holonomy class of the concatenation. I don't know if there's any questions about these examples or the definitions in general. Not, I'll go ahead. Okay, so just to imagine a little bit better how these examples might look like, we can think of what's the structure that Lie groupoids have. First of all, any Lie groupoid defines an equivalence relation on the base. So in a way, they're very much suited to study situations in which we have geometric equivalence relations, just like for Lie group actions or foliations or submersions. The equivalence class of a point is going to be given by all the other points connected to that one by an arrow, and it's called the orbit through that point. And for each point, I will have a Lie group, or I will have a group of arrows that start and end at that point. All of those can be composed because they have the same source and target. That's going to be called the isotropy group. And this group is going to be a Lie group, and the orbits are always going to be at least immersed submanifolds. And there's a little bit more structure, but we won't need it really. But let me tell you at least that, that the fiber via the source map of any point is always going to be a principal bundle with structure group, the isotropy group, and the projection is going to be the target map onto the orbit. Here there should be the orbit of X. So maybe yet another way to imagine how a Lie groupoid looks like is that it's a family of principal bundles with varying structure group, varying base, well, and varying, well, the total spaces stay the same, at least in connected components. Well, no, they might not. They various fibers of a submersion. But so again, you can think of a Lie groupoid as a family of principal bundles varying, and this family is indexed by the orbits of the Lie groupoid. And if you take the space of equivalence classes, you get something called the orbit space. And these orbits, they form what's called a singular foliation. So they look like a foliation in which the leaves might jump dimension, but look like a foliation in the sense that it still gives you an involutive distribution. So just to give you some idea for the examples I presented, what could these pieces look like? Let's say, for example, for a Lie group, the isotropy would be the group itself, and so would be the source fiber, this principal bundle. And so the orbit will just be a point, and the orbit space is again just a point. For a submersion, for example, there's no isotropy. The isotropies are trivial groups. The source fibers are going to be the fibers of the submersion, and so are the orbits. And then the orbit space will be the base of the submersion. For example, here in the action case, my isotropy groups are going to be the isotropy groups for the action, or stabilizers. The source fibers are all isomorphic to the Lie group itself. The orbits are the orbits of the action, and the orbit space is the orbit space of the action. So this is where the nomenclature comes from. While for the foliation groupoids, what we have is that the orbit spaces will be the leaf spaces, the orbits will be the leaves of the foliation, and here we'll have different principal bundles over the leaves, depending on what groupoid we're taking. If we take, for example, the monodromy groupoid, then the source fibers are going to be the universal cover of the leaves, and the isotropy groups are the fundamental groups of the leaves. While if I take the holonomy groupoid, I will have another cover of the leaves called the holonomy cover, and corresponding isotropy group, which is the holonomy group of transformations that start and end at the same point. Okay, just to give you an idea of what sort of geometric pieces might be involved here. And yeah. Okay, so now I want to tell you a little bit how would one use a Lie groupoid, and then go towards deformations. So in differential geometry, there's many uses, also not just in differential geometry, but I'm going to focus on this. In differential geometry, one of the main uses is, as I mentioned before, they are used to integrate infinite dimensional objects, infinite dimensional Lie algebras. And so Lie groupoids come with this vector bundle, a Lie algebroid that is their infinitesimal counterpart. And very often it functions as a good substitute for the tangent bundle of a manifold, but that is a little bit more adapted to the structure that you want to study. Let's say that we wanted to study foliations, then we could, instead of using the tangent bundle, use the distribution TF, which is going to be the Lie algebroid associated to both the holonomy and the monodromy groupoid. And this is a vector bundle. It has a Lie bracket in the space of sections. This has a Lie bracket in the space of sections, and it will substitute TM very well for many purposes. For example, there's foliated cohomology instead of just the Ham cohomology, but etc. You can do a lot of geometry with TF instead of TM. And one general philosophy for how to use Lie groupoids is the following. Since Lie groupoids generalize many different geometric structures, we can start with a certain structure we know well, for example, actions, take some theorems or some results that we know about actions, try to generalize them for Lie groupoids, and then specialize them again to try to obtain new results about, say, foliations. Of course, this is true of any generalization. Like, this is what category theorists hope categories do often. And it does not always work out well, but in some cases it does. And I'm going to tell you today of an example where it does with foliations, with deformations. So when I talk about deformations, I'm really thinking of 1 perimeter smooth deformations. So just to give you examples first, this is something I would consider a deformation of a Lie group. Start with the Lie group, which is the Cartesian, just the product of the Lie group of positive reals with multiplication and reals with addition. And define this new or this varying multiplication with respect to a parameter epsilon to be, on the first factor, I still just have the multiplication of my positive numbers x1 and x2. On the second factor, instead of just having y1 plus y2, I'm going to twist a little bit this, this product by something depending on epsilon. You can check that this is still, for each epsilon, this is still going to be a group law. It varies smoothly with respect to epsilon. And you see that, for example, at time 0, epsilon equals to 0, we do have an abelian group, while at different times, the group is no longer abelian. So again, we have a sort of a structure that we just change a little bit, like in the Kronecker foliation, and it becomes very different. It went from abelian to non-abelian. The example we had before of a foliation on the torus. So if we just have the Kronecker foliation and let's say that we had the Kronecker foliation by circles, so really just by the first factor of the torus, this one in blue, and we tilt by a small epsilon, we get a family of foliations that goes through foliations by circles and foliations by dense lines. Now, how do we generalize a theorem from deformation theory from groups to groupoids and then go back to foliations? We start with the following theorem from Palais and Stewart from 1960, quite classical. Smooth actions of compact Lie groups on compact manifolds are rigid. What this means is that if I start with any compact Lie group and have any smooth deformation of an action of it on any compact manifold, I cannot deform it. At least not in this sense of if I have a smooth 1 parameter family of actions like this, they're always going to be by isomorphic actions to the one I started with. Okay. And the way Paley and Stewart proved this was by first taking some infinitesimal representative for these deformations of actions, and then taking averaging of those infinitesimal deformations with respect to a Haar measure for these Lie groups, which exist because it's a compact Lie group, and it's a bi-invariant Haar measure because it's a compact Lie group. And using that averaging, they produced flows that take the deformed or the wannabe deformed actions. Actually, they just flow them back to, these flows are going to be by equivariant diffeomorphisms. So they will show that they will, what's the right word? Intertwine the action at time 0 and at time epsilon, showing that actually they were always the same action all along. Now, in joint work with Marius Kreinig and Ivan Strushiner, we proved that this generalizes to groupoids. So if we start with any compact Lie groupoid, which additionally is Hausdorff, something that in general we don't always ask that a Lie groupoid is, but if we start with a compact and Hausdorff Lie groupoid, it's always going to be rigid. No matter how much we try to deform it, it stays isomorphic. And this was also proved independently by Matias Del Hoyo and Rui Loja Fernandes. They used more Riemannian geometric techniques. The way we did it was in a similar way to Paley and Stewart. So what we did was use averaging with respect to a Haar system, which is the analog of a Haar measure, but for Lie groupoids. Now, to be able to do that, we needed to figure out what do we want to average. And what we wanted to average is, again, the infinitesimal representative of a deformation. And that turned out to be a cohomology class, like usually happens for deformation theory. I'll get back to this theorem and how to prove it in a while, but let me just tell you a bit of the punchline, which is not due to us, but I think it's really cool. It's a very, very nice application, which is that out of this, you can get a rigidity result for foliations. And just as a caveat, it's not the only way to do it. The authors did it also in a different way, but you could get it out of our result. So it's going to be a rigidity result for compact Hausdorff foliations, which are foliations for which all the leaves are compact and the leaf space is Hausdorff. So they're quite nice foliations. So when you have a foliation like that, and they were studied in these papers, I think this is funny, this paper, Foliations with All Leaves Compact of Edwards and Millet and Sullivan, and this other paper also called Foliations with All Leaves Compact by Epstein. I don't think I've ever seen these in any other context, two papers with exactly the same name. And foliations like that always have finite holonomy groups for every leaf. And out of the Hebb stability theorem, they're going to have very nice local descriptions of neighborhoods of every leaf. And these nice neighborhoods are going to be built out of a certain cover of the leaf, a transversal to the leaf, and the holonomy group of the leaf. They're actually an associated bundle. So this is a bit like a tubular neighborhood theorem, but for foliations of this type. This covering is the covering corresponding to the group, which is the holonomy group. And so you get a very nice description for them. And if M is a connected manifold, and we have a compact Hausdorff foliation on it, then some of the leaves will have no holonomy, so they will have a trivial holonomy group. This will actually be most of them. It's like a dense set. And all of those are going to be diffeomorphic to a generic leaf. Let's call it L0. Okay. So in this context, Del Hoyo and Fernandes proved some years ago, 3 years ago, that if you have a compact and connected manifold and a compact Hausdorff foliation on it, then the foliation is rigid if and only if the first de Gram cohomology or the first cohomology of the generic leaf is 0. Okay, so it's a criteria, a complete characterization of rigidity of compact Hausdorff foliations on compact connected manifolds. And note that it's only in terms of cohomology. The whole theorem does not mention anything to do with Lie groupoids, but the proof does use heavily Lie groupoids. Actually, they provide two different proofs, and both use Lie groupoid theory. And again, being rigid means that we can flow back the whole deformation to a constant deformation that changes nothing. Okay. I don't know if there's any question about this, about anything. You can ask me anything at any point. I just really want to stress that this is one of my favorite things when you get a theorem, which is about some classical geometric object like compact Hausdorff foliation, and you get to use Lie groupoids to prove nice things about classical geometry. Okay, so there's two possible proofs. I will try to give you a sketch of at least one of them, the one that uses our results. So first of all, one can use the following proposition. A foliation on a compact Hausdorff, a foliation on a manifold is going to be compact and Hausdorff if and only if the holonomy groupoid is Hausdorff, to start with, and has a proper source map. Proper meaning that the pre-image of compacts is compact. So in particular, for example, if M was also compact, then the holonomy groupoid would be Hausdorff and compact, right? And for those, we do know that we have a rigidity result for those types of groupoids. And their result starts with a compact connected manifold. So it starts looking like we could use our rigidity result for Lie groupoids, for compact Hausdorff Lie groupoids, to obtain a rigidity result for compact Hausdorff foliations on compact manifolds. Hopefully we could do this because if we do have a deformation of a holonomy groupoid, then we do have a deformation of the manifold on the base. However, the problem is that in general, it's not true that the deformation of the foliation induces a deformation of the holonomy groupoids. Because for each time, if we are changing the foliation, at each time we do have a holonomy groupoid, but then they might not fit well with each other. They might not very smoothly. On the other hand, and this is explained in the paper of Del Hoyo and Fernandez, if you are in the conditions of this theorem, so for a compact connected manifold and a compact Hausdorff foliation, if you take a deformation, then it will induce a deformation of the holonomy groupoid. And then our rigidity result will imply the rigidity of the foliation. Or rather, we can go through our rigidity results to prove that the rigidity of the foliation is equivalent to H1 of the leaf being 0. That's the correct statement. Okay, so now I'll tell you how one would prove rigidity of Lie groupoids, and I'll try to be brief. So in general, deformations are controlled by cohomology. Like classical examples would be, for example, for associative or Lie algebras, you have Hochschild or Lie algebra cohomology with values, for example, in the adjoint representation. And for complex manifolds, this was a big part of the motivation for our work. You would get Dolbeault cohomology controlling the formations of complex structure. But also for foliations, you do have a cohomology controlling the formations of foliations, which is called Heitsch cohomology. And there is this Lie group action cohomology of Palais-Stewart, which is the group cohomology of the acting group with values in the module of vector fields on the acted upon manifolds. And this is kind of the one we used to generalize the averaging methods. For a Lie groupoid, we are also going to get the deformation cohomology that we use to prove the rigidity results. The way it's built is as follows. First of all, it's going to be similar if you have ever seen to group cohomology, but I will explain it a little bit. So for a Lie groupoid, we can build a sequence of manifolds called the nerve. It's actually going to be a simplicial manifold, but it's a sequence of manifolds Gn, which are going to be the manifolds of composable n tuples of arrows, right? So they're going to be, for example, here I have G0, G1 up to Gn, and I'm taking the source of G0 to be the target of G1, etc., so that they're all composable. And I have maps taking n+1 tuples of composable arrows to n tuples of composable arrows by either forgetting the first arrow or forgetting the last arrow, or simply composing a pair in the middle. And these maps together behave like the face maps of a simplicial object. And this is all not terribly important, but what that really means is that if I take their alternated sum, I get a chain complex. Or rather, I would if this would be vector spaces and if I could take their alternated sum. That does not really make sense what I said, I'm sorry. What makes sense is I could take smooth functions, for example, or other sorts of functions, so smooth functions on these GKs with targets, in this case, TG, that Lie groupoid I told you about in the beginning, and then I can take more or less the alternated sum of those face maps. That won't really work for what I want, so I'll have to do some modifications, but it's not too different from doing that. The technical details, I think I will skip them, but the main point is the deformation complex of a Lie groupoid will be composed of maps from k tuples of composable arrows to the tangent bundle of G, and these have a differential that uses these face maps. Now, I just want to look at what happens in some particular degrees. For example, if I just add k equals to 1, what I'm asking are for maps from G to TG, and I'm going to also ask that the map takes G1 up to GK, this string of composable arrows, to something living in the fiber above the first arrow. So in degree 1, I'm just asking for a vector field. Okay. Now, some nice things are that, maybe let me tell you already that the k equals to 1 co-cycles, so a vector field is going to be closed if and only if that vector field is what's called multiplicative. So it's a groupoid morphism from the groupoid G to the groupoid TG, which is useful because for those vector fields, the flow is by Lie groupoid isomorphisms. But I will go back to it when I need it. So now, how would we use such a deformation cohomology to study deformations? Well, a deformation is a family of Lie groupoids smoothly parameterized by a real parameter. You can make sense of these, if you want, formally, by putting these G epsilons as fibers of a submersion. So one would take, this is inspired by complex geometry, one would take a Lie groupoid G tilde over an interval also seen as a Lie groupoid, just with arrows, unit arrows from each object to itself and no more arrows. And we ask that we have a submersion of Lie groupoids from this big groupoid G tilde to the groupoid of units of the interval. If we have a groupoid submersion, then each fiber will not only be a submanifold of G tilde, but actually a Lie subgroupoid of G tilde. They are going to be these G epsilons. Okay. And the deformation is such a family such that the fiber over 0 in this interval is precisely G. That's a deformation of G. Okay. Now, if I have the deformation of the groupoid, I'm going to have varying structure maps. And so I can get elements in my cohomology which are going to be given by the infinitesimal variation of the structure maps. Very explicitly, for a particular nice kind of deformations, let's assume, for example, that all the fibers look like each other. So the family is trivial as a family of smooth manifolds, but not as groupoids. This is analogous to deformations of complex manifolds, where you would have deformations which are trivial as smooth manifolds, but not complex manifolds. Let's say that we have all the fibers the same as smooth manifolds, and also all the source maps always the same as the source at time 0. Then I could define a cocycle which takes a pair of composable arrows and just multiplies GH at time 0, inverts H at times epsilon, and multiplies GH with this inverse again at time epsilon. So at time 0, I would be multiplying GH with H inverse. That should just give me G. If the deformation does not change, then I would always get G. I would get a constant path, so the derivative at time epsilon would be 0, right? So if I had a constant deformation, I would have a trivial cocycle. I would just have 0. If I have a different deformation, this will define a curve. This multiplication will define a curve in G. So taking its tangent vector at time 0 will define me a vector in TG, which is exactly what I needed. I needed something that takes 2 composable arrows and gives me something in TG. This is how I'm going to define the deformation cocycle for such deformations. And there's a way to define them for any deformation in this sense that coincides with this simpler definition in this simpler case of deformations that keep the manifolds fixed. Okay, just to give you an idea that really I'm encoding variation of the multiplication, basically. So the deformation cocycle is of this form. And what will happen is, we know that if the deformation is trivial, I get a constant curve, so I get a 0 tangent vector. But conversely, the one thing to check, first of all, is that this will actually define a cocycle, not just a cochain, and that will be a consequence of associativity. The cohomology is built in such a way that these will be a cocycle because each of the m epsilons is associative. And now what one would check, these are all different lemmas, is that if my cocycle is actually co-boundary, then it's going to be the differential of a certain vector field. And that vector field will be such that if I sum dd epsilon to it, will be a multiplicative vector field. This is yet another lemma. What that means is that if I started with a deformation that has trivial deformation class, then I can build a vector field such that this x is tangent to the fibers of the family. The dd epsilon takes a fiber to the next fibers. Well, it moves along the fibers. And the sum of these two vector fields is going to be by groupoid automorphisms. As long as I can flow, that will give me isomorphisms between the fibers of my family. It will trivialize the deformation. If the groupoid I'm trying to deform is compact, then this flow will exist for all time, or at least for uniform time on G at time 0, at epsilon equals to 0. And I can prove by averaging methods with a Haar system that exists for compactly groupoids, similar to the bi-invariant Haar systems for compactly groups, that actually for compactly groupoids, every deformation cocycle is going to be trivial. So I can build a vector field and I can flow, so I can trivialize, so the deformation is trivial. Okay, so that's the sketch of the proof of how compactly groupoids are rigid. They cannot be deformed. And that then leads to the deformation, to the rigidity theorem for, or the rigidity criteria for foliations. I think perhaps I will sketch the other proof that they provide. And since my time is kind of short, I will just tell you, a little bit more about other properties and some applications of this deformation cohomology and this deformation theory. So first of all, this deformation cohomology is what's called a Morita invariant. So what that means is that it's an invariant associated to the orbit space of the groupoid. So this gives a cohomology associated to differentiable stacks, these sort of singular spaces that are described by Lie groupoids. Another thing is that for Lie groups, the deformation cohomology was really groupoid cohomology with values in the adjoint representation. For Lie groupoids, the adjoint representation is very subtle. You need to make some choices of connections to be able to define them. And the deformation cohomology is still going to be isomorphic to the cohomology with values in a sort of adjoint representation. But here we have the advantage that we have an intrinsic model for it. And one possible problem with the theorem I presented, I like it a lot, but maybe there's not so many compactly groupoids. But one good thing is that we can actually use relative versions of our rigidity theorem to look at neighborhoods of compact subgroupoids of bigger groupoids which are not compact themselves. So that will give us normal form results, a bit like that normal form result that I showed for foliations using a transversal, the holonomy group, and a cover. We can get similar results for neighborhoods of compact subgroup, some compact subgroupoids of what are of proper Lie groupoids, so much wider class of Lie groupoids. And recently, together with Ivan Strushiner and Christian Cárdenas, we've been developing, or we developed some deformation cohomology and studied the moduli space a little bit of symplectic groupoids, so groupoids compatible with a multiplicative symplectic structure. In a similar vibe, there's a study of the deformations of multiplicative contact structures, so Lie groupoids with a contact structure. This is by Camilo Angulo, Maria Amélia Salazar, and Daniele Sepe, also recently, and they prove a gray stability theorem for these groupoids. And I know Ivan and Christian Cárdenas are also developing a paper on the formation theory of morphisms of Lie groupoids. There's papers by Pierpaolo Vitaliano and Pierpaolo Lapastina and Luca Vitaliano on the formations of vector bundles over groupoids. So it's a growing field, I would say. And perhaps I'll stop in a minute, but just to let you some big open problems on these theories. On deformations, the biggest open problem, I would say, is how to find the DGLA that has underlying complex, the deformation complex. Because for all the other examples that I mentioned, or most of the other examples that I mentioned, like foliations or complex manifolds, you really have a differential graded Lie algebra controlling deformations. We do have a chain complex, but we're missing the Lie bracket, and it's really not easy to find, not even for Lie groups. That's very surprising for me, because these things have been studied since the 60s and no one knows. There's also questions about finding rigidity results with respect to topologies in the space of structures. So if I have a groupoid and a groupoid nearby with respect to some sort of Whitney topologies, can I guarantee that the nearby groupoids are going to be isomorphic? I don't know about that. There's some questions about the study of some properties stable under deformations. So when I have a groupoid which can be deformed, which things are preserved about it? And one of my PhD students, Sebastian Daza, is now studying the possible stability of subgroupoids under deformations. And another very big problem is, okay, when I told you that Lie groupoids integrate certain Lie infinite dimensional Lie algebras, when can one of those be integrated by a Lie groupoid with compactness properties? That would be very interesting to know. And for people maybe interested in non-commutative geometry, there's a long search for an index theorem for Lie groupoids. People know how to do it longitudinally, transversally, but not both of them at the same time. And this would be like a panorama of some big questions. Thank you a lot, and sorry for the delay.
Thank you, João, for the talk. This was very interesting for sure. Does anyone have any question? If not, let's thank João again.
Thank you.
In chat or interaction or through video or microphone. Thank you, João.
Thank you.
Next is Carolina Lemos de Oliveira. Hi, Carolina. Do you need are you ready? Do you need a couple minutes?
Yeah, I'm ready. But if you want to take a little break, it's not a problem for me.
Does anyone need like a minute or two, or we can start? We can start, right?
Okay. So let me try to share. Okay. Let me. Okay. Can you see?
Yes, we can see.
And it's passing the.
Yes. They're transitioning.
Okay. Yes, just okay. So it's okay, right. I'm ready.
Okay, so next we have Carolina Lemos Oliveira from EMPA. And her talk is titled Transverse Foliations for Web Flows on the Tide Tree Sphere. Thank you, Carolina. You can start.
Okay, thank you for the invitation. So I talk about transverse foliations for web flows. So around half of the lecture will be to explain this, what are web flows and what are transverse foliations. So the only thing I don't need to explain is the tree sphere. So later, when I have explained it, everything, I will state my results. So basically, for any flow, smooth flow in a tree manifold, the idea of transverse foliation is kind of a generalization of global surface of section. So since I think not everybody knows what is a global surface of section, I will define it first, so then I can explain what is a transverse foliation. So the idea of a global surface of section is the following. We are in a tree manifold, right? And we have a flow, a smooth flow in it. And the idea is that we have surface, so a two-dimensional thing. We have a surface that can have boundary. And if it has boundary, the boundary consists of periodic orbits of the flow. And in the interior of this surface is transverse to the flow, and all the orbits of the flow intersect it. And if you take any point in your tree manifold, the orbit passing in this point will intersect this transverse foliation infinitely many times, both in the future and in the past. So we have a well-defined first return time. You take any point here, then you consider the time when it returns to the transverse section, and you can define a first return map. So a map defined in this transverse section. So you take a point and sends it to the first point when it returns to the section. So the idea is that you can simplify the flow. You can understand a lot of properties of the flow just by understanding the dynamics of this first return map, that is discrete dynamics in the two-dimensional surface. So that's why it's very interesting. But of course, it's very good to have a global surface of section, but it's very hard to find too. And in general, we don't have it. So the idea of a transverse foliation is some sort of generalization of a global surface of section. And it's also defined for three-dimensional flows. And I forgot to mention, it's defined for both global surface of section and transverse foliation are defined for flows that have no rest points. Okay. So if you have a three-dimensional flow, the idea of a transverse foliation is the following. You have a special set of periodic orbits that we call the binding orbits. And in the complement of these orbits, we have a lot of transverse sections that are not necessarily global, are just surface transverse to the flow. And these surfaces, they form a foliation of the complement of these orbits. And each of these leaves have boundary on these special binding orbits. So the idea, it is a kind of generalization of global surface of section, because you not necessarily have just one surface, but your manifold is foliated by these surfaces, and sometimes you can obtain some properties of the flow by this. So in this picture here, the idea of this is that it represents a three-dimensional object. You can think of this as you can think of an axis here, and if you rotate this picture around this axis, you will have like an orbit here, okay? And these guys here will be a one-parameter family of disks. So it is defining family of disks, okay? Actually, you can, I forgot to mention. So this is, you can think of this as S3, as R3 with an point in infinity. So you can think of this as R3. And so, okay, this is an example of a transverse foliation. Actually, this guy here is an open book decomposition of S3. So you can also think of a transverse foliation as a generalization of an open book adapted to your flow. And this guy here is more complex. So you have actually, if you think the same as of an axis here, and you are rotating around this axis, you have three orbits here, three binding orbits, and you have a lot of some different families of leaves. So here you have a family of disks that is parameterized by an interval. You have one disk here. Here it will be a cylinder. This guy here will be a cylinder. This guy here will be a cylinder too. And it's forming and in the interior of this region here, you have a lot of cylinders, okay? And so you can also find this kind of objects by the name of systems of transverse sections or broken book decomposition, as that, because they generalize the open book decompositions, okay? So now that we have defined transverse foliations, I will define the other ingredients that are the red flows. And as I will explain later, red flows are closely related to Hamiltonian flows and to symplectic Hamiltonian flows and symplectic manifolds. So the definition of a red flow is the following. If you have a contact form on a tree manifold, actually it works for any dimension, but I will just talk about dimension 3 here. So if you have a contact form that is one form in your manifold that such that lambda wedge the lambda is on volume form, and so this any contact form defines contact structure. It's a plane distribution, okay, given by the kernel of your contact form. And this one form also defines a vector field called the red vector field, because the kernel of the lambda is one-dimensional. So if you can define one direction by saying that it's in the kernel of the lambda, and we define the red vector field by normalizing it, saying that lambda in R is identical to 1. Okay, so it defines one vector field and called the red vector field. And the red flow is just the flow of this red vector field. And it's intimately related to symplectic geometry and Hamiltonian dynamics. Because if you have any symplectic manifold and Hamiltonian function on it, then you can define the Hamiltonian vector field by omega and x in the Hamiltonian field is equal to the differential of the Hamiltonian. So you can, it's easy to check that the Hamiltonian is constant along the orbits of the Hamiltonian flow. So you can study in dynamics restricted to energy levels, because all the orbits lies in energy levels. So when you have a special kind of energy level that's kind of called compact type hypersurface, the definition of this is that you have a transversal vector field in a neighborhood of your surface that is an Liouville vector field, so such that the Lie derivative of the contact form in the direction of this vector field is the symplectic form, is the symplectic form. And so if your energy level is contact type, then you can show that this energy level is a contact manifold, and that the Hamiltonian vector field is in the kernel of the lambda, of the contact form. So since the kernel is one-dimensional, this means that the Hamiltonian vector field is parallel to your Hebb vector field. So basically you can, if you want to study the dynamics of Hamiltonian vector field, if you restrict it to a contact type regular energy level, you can, it's the same as studying the Hebb dynamics of the associated Hebb vector field, because they have the same orbits up to parametrization. So that's the idea. And also we have the opposite. If we have a contact manifold and Hebb vector field on it, we can see it always as an energy level of Hamiltonian, special Hamiltonian. So that's why they are very related. So I will talk about a special type of contact forms on S3 that are called the tight contact forms. And the definition is the following. I will not explain exactly what is a tight contact form in general, but in S3 they are very simple to define. So if we have this canonical one form, the Liouville one form, defined this way, and we consider it restricted to S3, and so it is a contact form in S3, and it happens that the contact structure defined by lambda 0 by the Liouville form is a tight contact structure. It's actually it has been proven that it is the only tight contact structure on S3, so we can call it the tight contact structure on S3. Okay, so every time I talk about the tight S3, it's S3 with this contact structure. Okay, so if we consider any Hamiltonian on R4, and we want to study the dynamics restricted to an energy level that is star-shaped. This means that the half line is star-shaped with relation to the origin. This means that the half line starting in the origin just intersects your energy level once and transversely. So if you have an energy level like this, the canonical contact form defined here is equivalent to a form of the kind F lambda 0 in S3. We can consider a diffeomorphism that takes this guy to this guy here, and under these diffeomorphisms, the dynamics of the Hebb vector field here will be equivalent to the Hebb vector field of some F lambda 0 in S3. So studying the Hebb dynamics of any star-shaped regular energy level is the same as studying the Hebb dynamics of S3 with this tight contact form. Okay. So before stating some results about this tight contact vector field, head vector fields in S3, I just set some notations and definitions. So the idea is that every time we are one thing that we want to know is about the existence of periodic orbits, for instance. And every time we talk about a periodic orbit, I will consider it together with a period. In general, it will be the minimal period. When I'm considering the orbit with the minimal period, I call it simple. It's an embedded orbit. So we'll be interested in the linearized flow. Actually, if you consider the derivative of the flow and restrict it to the contact structure, it will be a symplectic map. And when I consider it t, and when t is the period of my orbit, I will call it this map the linearized return map here. Okay, and I say that an orbit is non-degenerate if one is not an eigenvalue of the linearized return map. And we say that contact form is non-degenerate if all the orbits are non-degenerate. And the idea is that in general, non-degenerate contact form are easier to work with. But they are very hard to appear in applications. And associated to a non-degenerate orbit, we have an index called the Conley-Zander index that is defined by this linearized flow near this orbit. I will not define it precisely, but the idea is that it's related to the winding of this guy here, x0. The linearized flow applied to any vector in R2. Of course, with respect to some trivialization, we need a trivialization to define this. And the idea, it's not exactly the winding, because when we vary this guy here, we vary the winding. But the fact is that this one, for varying this V in R2, the fact is that we have a winding interval. This guy lives in an interval, and the length of this interval is smaller than 1/2. So the idea is that, let's say, this guy here. So we can define an invariance, that is the Conley-Zander index, by saying that, for instance, we have, let's see, for instance, the index that we use, like if we have some V such that this winding is 1, I say that this guy has Conley-Zander index 2. And if all the windings are bigger than 1 but smaller than 2, then the index is 3. These are the two indices that are important here. So basically, this is the idea. And so the first result involving the existence of transverse foliations for Hebb flows on ST was this theorem by Hofer, Wisocki, and Zander in 1998. So they proved that when your Hebb flow is dynamically convex, meaning that the Conley-Zander index of all orbits are bigger or equal than 3, and in particular, if you have an energy level of Hamiltonian that is strictly convex, I mean, is the boundary of a strictly convex region, or it's the same as having positive curvature, then it's dynamically convex. So You can think of this as Hamiltonian flows in dynamically convex and strictly convex hypersurfaces. So in this case, there exists an open book decomposition where every page is a global surface of section of the flow. So we have the best scenario possible. We have global surfaces of section, and they are very simple. They are just disks. So also it's a result about tight contact form, because the same authors have proved that if you have a dynamically convex flow, then it's associated to a tight contact form on S3. And so this was the first paper when the idea of transverse foliation appeared, but the name was not necessary because in this case it was an open book. So some question that appear after this result is which orbits can be the binding orbits of global surface of section of this kind. So some results by Riniewicz and Salomon between 2008 and 2011 are the following. They characterize which orbits can be binding orbits of open book decomposition. And the idea is that if you find the orbits with these properties, then you know that it has an open book with boundary in it. And basically, in the dynamically convex case, the only necessary and sufficient condition is that P is a knot, is a trivial knot, and this condition, that S self-linking number of P is -1, it's an invariant related to knots transverse to the contact structure. But basically, when you have, every time you have disk transverse to the flow with boundary in your orbit, it has a self-linking number -1, but I will not explain the details. And basically, in general, if you don't have the dynamical convexity, they proved that the necessary and sufficient conditions for an orbit to be the boundary of a global surface of section of diffeomorphic to a disk is that the Conley-Zender index is bigger or equal than 3, self-linking number is -1, and all the orbits with index 2 is linked to P. It's like the existence of this orbit with index 2 not linked to P is exactly the obstruction to the existence of these global surfaces of section of disk type. Okay, so later in the beginning of the 2000s, Hofer, Wisocki, and Zender, they proved that they generalized that first result, and for any tight contact form on S3. And basically, they proved that when you have a tight contact form that's non-degenerate, in the previous result, it was not necessary to assume non-degeneracy, but here they have to assume. So the Rev flow always admits a transverse foliation, not necessarily a global surface of section, but always admits a transverse foliation. And in this existence theorem, they showed that the transverse foliation, the binding orbits always have always an index in 1, 2, or 3, self-link number 1, and the ellipse have G 0. They are disks with some finite set of punctures removed. But in general, given one Hamiltonian flow, you don't know. You know that there is some transverse foliation, but you don't know how your transverse foliation looks like. So one of the directions after these results is, of course, can generalize it for other manifolds, but but even if you sorry, I forgot to mention it has been generalized for any tree manifold recently by by Colin, De Hornoy, and Hedshep. But what I want to talk about here is still on S3, that the idea is that other question is, given a Hamiltonian flow that you define in application, in some application, for instance, how do we know what kind of transverse variation does it admit? And some, in general, we are interested in contact forms that are degenerate. They naturally appear on applications. So also we wanted to know, given some head flow that can be degenerate, which does there exists a transverse variation, and how does it look like? So of course, in that previous result, we know that in the dynamically convex case, we have open books that where each leaf is a global surface of section. But the first result involving transverse variation that is not an open book was a paper by Nayara de Paula and Pedro Salomon in 2013. And I will not state the theorem because it would take too long. But the idea is that they defined a foliation called 3-2-3 foliation. It has 3 binding orbits. And it was the first known examples of transverse foliation that are not open books. And they showed that existence of this foliation for some energy levels of Hamiltonians near saddle center critical level. And the contact form they considered were degenerate, so it makes things even harder. And also they are weakly convex contact form. They have the Conley-Zender index of every orbit is bigger or equal than 2. Okay, it's less restrictive than dynamically convexity, but it still has some restriction. So all these results I talked about are the proof of all these results involves pseudo-holomorphic curves in symplectic manifolds. Of course, I don't have time to explain everything, but let's just give an idea. The pseudo-holomorphic curves we are interested here are defined in non-compact domains and have codomains that are also non-compact. Okay, so we can, given the lambda compatible complex structure in this symplectic bundle given by the contact structure, we can define a special almost complex structure on these manifolds that we can make symplectic manifold, R cross S3 or R cross M for any contact manifold, that is especially defined to our purposes. So the idea is that when you restricted it to the contact structure, it is the J you started with. And when you apply it in the R direction, it gives the head vector field. And of course, I want it to J squared to be minus identity. So when I apply it in R, it will be minus the direction of the real direction. Okay, so we are interested in pseudo-holomorphic curves. J holomorphic curve is with respect to this J tilde here. So okay, of course we want to study maps that satisfy the generalized Cauchy-Riemann equation, and also has finite energy that is defined this way. The idea is that it's, of course I will not explain everything, but one of the most important things is that this a result that was proved by Hofer, I think, in 1992 or 3, I don't remember well, is that because the way you define this almost complex structure, when you consider holomorphic chart very close to one puncture, like we are considering pseudo-holomorphic curves defined in a Riemann surface, a compact Riemann surface without a finite set of punctures. So when we consider a chart, holomorphic chart very close to this puncture, we can write the points here are as like this, parameterized by S and T. And we can also write the real part of our curve and the part in the manifold, in the contact manifold. And what happens is that this part, this projection in the contact manifold approaches on periodic orbit when you approach the puncture. So basically, the existence of these finite energy curves, so the holomorphic curves, imply the existence of periodic orbits and vice versa. So this was one of the ideas. And of course, we have a lot of nice properties of these curves that so that we can define these transverse foliations as projections of these pseudo-holomorphic curves to the contact manifold. And basically, I cannot explain everything, of course. But the foliation, the kind of foliation that I'm interested in is called the 3-to-1 foliation. And the idea is that it can be defined for flows that are not have colonies in the index 1 orbits. Actually, have no restriction to colonies in the indices. And the foliations looks like this. We have 3 binding orbits that are, as I said in the beginning, you can think of these as, you can think of an axis here, and you can rotate it to visualize the foliation. So we have 3 binding orbits here that you should see like exiting the screen and entering the screen here. So 1, 2, and 3. And they have colonies and indices like 1, 2, and 3. And basically we have in our ellipse are this family of disks here, family of cylinders here, and these 2 cylinders, one here and one here, and also this cylinder here and this disk here. Okay, we can also define for any transverse foliation some orientations. We can ask in the definition that the leaves are oriented such that the orientation of the leaves and the orientation of the flow gives the orientation of your manifold. Okay, so with this definition, you can say what are, let's say, negative asymptotic limits and positive asymptotic limits. Like here, this guy is positive and this guy is negative, for instance. But for this leaf, this guy is positive. Okay. And okay, basically that's the idea. And the reason why I'm interested in this is because it's the simplest possible foliation that has index 1 binding orbits. So this is the first step, let's say, before studying more complex foliations. Okay, so the result I will state is about the existence of this kind of foliations. And we will assume that we a priori know the existence of the binding orbits. And the idea is to give some sufficient and also some necessary hypothesis to the existence of a 3-to-1 foliation with binding orbits in this special set of orbits. So the idea is the following: we consider tight contact formula on S3, and we assume the existence of three special orbits that are non-degenerate and have the appropriate collision index indices, and have periods satisfying this. The period of the index 1 is smaller than the period of the index 2, that is smaller than the period of the index 3. And all the orbits are trivial knots, and they are not linked to each other. Of course, it's it's immediate to see that these are necessary conditions for the existence of a trivial foliation, the way I define it. Because the only one that's not obvious is maybe this, but since we are considering sections that are transverse to the flow, this will be implied by this. So, but the rest is very, very obvious from the definition. And basically, another hypothesis that I will do is that we don't have an object like this. We don't have a sphere with equator in the index 2 orbit. That is what we call a strong transverse section. It's not too important to understand the definition, but the idea is the following. These strong transverse sections, of course, are transverse sections, but they have more properties. And these are properties similar to projections of pseudo-holomorphic curves. Okay, and basically all projection of, if you have a projection of pseudo-holomorphic curve that is a transverse section, it will be a strong transverse section, but not necessarily every strong transverse section is a projection of pseudo-holomorphic curve. And the idea is that if we assume that this guy does not exist, we will assume this, of course, a priori, and it's not so crazy to assume this because this is also a necessary condition. It's okay. It's maybe not so hard to show that it's also a necessary condition. Actually, it's very. Oh, I'll not talk about the proof, but it's not a hard proof. But I will skip it. This is the same theorem. I was planning to talk about the proof, but I will skip it. And the idea is that if we assume all the conditions, and we assume that that every heavy orbit with period smaller than T3 is non-degenerate. So we are not assuming that everything is non-degenerate because it's very hard to check, but we are assuming that the orbits that have period smaller or equal than T3, that is will be a finite set of orbits, are non-degenerate. And if you consider just the orbit of period is sufficiently small, this special orbit with index 2 is a unique with only in the index 2 that's not linked to the orbit with index 3. And the orbit with index 1 is the only one with the index 1 that's not linked with the orbit with index 2. So if you assume this, and we know the existence of only one pseudo-holomorphic curve, pseudo-holomorphic plane, or that is, the image will be a disk, but the idea is that a pseudo-holomorphic curve with a domain in the complex plane. And if we know that there exists a pseudo-holomorphic plane asymptotic to P3, then there exists a 3-to-1 foliation with these binding orbits. And this was it's a modification of a result in my PhD thesis in 2020, but it's a little different here. And later I proved a similar result, but here without any condition on the non-degeneracy of the orbits. So it is, let's say, it's way harder to deal with degenerate contact forms. So we have to be more restrictive with the hypothesis. So if we assume that, we have to assume that the periods of these special orbits are close to each other in the sense that this is already necessary. So T1 is smaller than T2, that is smaller than T3, but we also have to ask that T3 is smaller than T1. And if you assume that P1 and P2 are the unique heavy orbits that are different from P3, with periods smaller or equal than P3, that are not linked to P3. That it means that if you take any orbit, either it is linked to P3 or it has big period, basically, except for P1 and P2. Okay, but in this case, since we're assuming that the flow can be degenerate, things are harder, and we have to assume not just the existence of one pseudo-holomorphic plane asymptotic to this orbit here, but we also have to assume the existence of one cylinder. So if you assume this, we can have all the foliation. And basically, the proofs of this two theorem involves the same tools from the theory of pseudo-holomorphic curves in simplicizations. And I cannot explain all the proof, but basically I can talk a little about the ingredients. And so we have a very rich theory for this finite energy pseudo-holomorphic curves. And basically three things that are mainly due to Hofer, Vysotsky, and Zender are in a lot of papers, mainly in the 90s and beginning of the 2000s, is these properties that we have a Fredholm theory for these curves. Basically, under some nice hypothesis, we know that these curves appear in families, and that they are we have a manifold of these curves, and we have a compactness a theory. Basically, we know if you include some broken curves that are not exactly pseudo-holomorphic curves, but that are let's say union of pseudo-holomorphic curves, we have these families are compact. So we know how they break. Like you know that they are manifolds, and you can describe the boundary, the boundary of these manifolds. And we also have a very nice intersection theory, and that's these three ingredients that are the main ingredients of the proof. The idea is that if we know the existence of one curve here, we can use Fredholm theory to show the existence of all these curves, and we can after some work describe how it breaks. And we know that this family will only break in one cylinder and one disk, but it could be could break in different cylinders and different disks. But the idea is that since we have the hypothesis of non-existence of transversal sphere, it can only break like this on a cylinder like this and a plane like this. And basically, intersection theory and Fredholm theory is what will make these guys really form a foliation. We know that we really have these leaves really form a foliation. And also this guy, this cylinder, he will come from compactness, but it's a little more complicated, but because we are considering other kind of almost complex structure, but basically with compactness, we can show the existence of this guy. And in this region here, we also use theorem called Buin theorem. Basically, the ideas of this guy is the same as in Morse theory. Like when you have a broken trajectory of something of index difference 1, we always have an actual trajectory very close to this broken trajectory. And this also happens with pseudo-holomorphic curves or finite energy pseudo-holomorphic curves. The idea is a kind of generalization of this. Like when you have two curves with the appropriate indices, or the appropriate Fredholm indices, and that have asymptotic limit in common, in this case, these orbits, we can really find actual pseudo-holomorphic curves very close to these orbits. And that's why we have all the foliation. But this is just an idea. Basically, let me just, it's more fun to understand on an example. So I have a very simple example. It will be a separable Hamiltonian. So it will be very easy to see the properties of this Hamiltonian. So in one, it's defined by with the parameters x1, y1, x2, y2. So you have one symplectic plane here and another symplectic plane here. So in this part, it is very simple. The energy levels will be circles. And in this other symplectic plane, it will be this polynomial, depending on 4 parameters. And another parameter epsilon, and the idea is that this epsilon will be very small. And basically, for appropriate parameters here, we have this function has exactly 3 critical points. This guy is a minimum. This guy is a maximum. This guy is a minimum. And this guy is a saddle point. So yeah, basically that's it. And for appropriate energy, for instance, I took 1/2 here. It's the energy level is a star-shaped hypersurface. You just need to compute the derivative of 8 in the radial direction. So to see that it's a star-shaped, it implies that it's a contact type energy level. So we have a lambda 0, which is a contact form. So we really have a contact manifold folded diffeomorphic to S3 that is equivalent to S3, the type contact form. And we can define the candidates to binding orbits just by this. Like we take these critical points and we take the associated orbits of their Hamiltonian such that they are in the appropriate energy level. Basically, what you see in the projections are these points, and in the other projection, these orbits. So for sufficiently small epsilon, they will really be very close. The periods will be very close. And it's easy to see that they are trivial link because you can really construct disks to these orbits that don't intersect with each other. It's very easy. Like, for instance, one disk here projects here, for instance. And computing the linearized flow, we can really see that they are non-degenerate and they have index 1, 2, and 3. Like this one have index 2, that's the saddle. The maximum has index 1, and the minimum has index 3. And basically, so some of the hypotheses are checked. And I will not explain a lot, but basically we can also check the hypothesis of non-existence of a sphere like this to the orbit P2. We can really show because basically the main idea is that on a sphere would be something like this. It will, we really know what are the invariant and stable and unstable manifolds, and they really divide your energy level in 2 regions. And you know that if you have something like this, it will enter this region here. But here the homology is generated by this P2, and it has to exit here. And the problem is that the invariant manifolds have the lambda area 0. And since you are assuming that this guy is a strong transverse section, it has the positive lambda area. So it will determine a curve here that has to, for one side, need to have a lambda, the integral of lambda had to be bigger than this guy, the integral of this guy here, but in the other side it has to be smaller. So we have a contradiction here, and it's very easy to see that we don't have this sphere. And also in this case, it's not so hard to find the existence of some of the pseudo-holomorphic curves, basically because of the symmetry of the problem. We can reduce the problem of solving the Cauchy-Riemann equations to a problem of solving an ODE. So it will be more or less easy. And basically, you can also check the hypothesis in the periods, because it's you can really see that all the orbits are linked to this guy here. Basically, just say it's easy to see in the picture that all orbits here project in these guys here. They will be linked if you consider a plane here, for instance, on disk here, sorry. And the only orbits that are not linked are these in this part here. And it's a property of Hamiltonian flows that when you have a small Hessian in some region, the periods of the orbits in that region will be large. So basically, you can show that in this part here, for epsilon small, the Hessian is very small, so that the periods here are very large. So there's no problem if these orbits are not linked with each other. So basically, you can check all the hypotheses of the theorem, the degenerate version of the theorem, and we can check everything. So we really have in this simple example intuitive foliation. And actually, in this example, we can really see the projection of the foliation here to look like this, like the orbits are here. And here we have a family of cylinders, a cylinder here, a cylinder here. And we have a family of planes that will be projecting these guys here, basically. So we can really plot the foliation in this case. So yeah, basically I will stop here. And of course, there's a lot of foliations to be studied. These are just like this 3 to 3 and this 3 to 1 were just the first foliation that has been studied. But in general, I want to know a lot more about how to apply this whole theory of transverse foliations to real to Hamiltonians coming from applications, right? So that's it. I will stop here. Thank you.
Thank you, Carolina. Does anyone have
some questions? I forgot to ask. Oh, it's
not. Thanks, Carolina, for your talk.
Okay. Let me stop sharing.
Okay. Next is Camilo Lazeras.
Hi, Bruno.
Hi, Camilo. How are you?
Fine, thank you. Shall I start to share screen? Yes.
Yes, please.
All right. All right. It's supposed to be sharing now.
Yes, we can see it.
All right. Hold on. The second slide can be seen for everybody, no?
Yes, it's the table of contents we see now. Now the title. Yes.
Thank you very much. All right.
Nice. Are you ready?
Yes.
Yes. Okay. So start, everybody. This is the last talk of the day by Camilo Lazeras from Universidade de Antofagasta, and his talk is titled "Type." It's 2B parabolic
2B.
Parabolic PQ string from non-trivial M2 braids. Camilo, you can start.
All right, thank you very much, Bruno. First of all, I would like to say good evening to everybody. It is a pleasure to be here at COMCA. I would like to thank the organizers for allowing me to give this talk, which is titled Type 2B Parabolic Peak String from Non-Trivial M2 Brains. This work was done in collaboration with María Pilar García del Moral and with Álvaro Restucia from University of Antofagasta. The outline of this talk, it is, I will start giving a brief motivation of why we are talking about this. Then I will give some, on the preliminaries, I will talk about some basic stuff about M2 brains and some improvements that have been recently made on the identification of non-trivial sectors of M2 brains. And on the third part of the talk, I will talk about the identification of sectors or objects of a string theory that may be related with these non-trivial M2 brains and its repercussions. At the end of the talk, I will give some conclusions about this seminar. All right, as a motivation, we know that in the universe that we live, there are 4 fundamental interactions that can describe all the forces that exist in the universe. These are the gravitational interaction, the electromagnetic interaction, the weak and the strong interaction. The first interaction, which is the gravitational, it is described by general relativity, which is a geometric theory. It is a theory that concerns about the geometry of a space-time, as we saw early today in the talk of Alan Cooley. And the electromagnetic weak and strong interactions are described by the standard model of particles, which is a non-abelian gauge theory described by a quantum field theory. The standard model of particles describes these 3 interactions among the basic and most elementary particles that conform matter. Like an example, these first 12 blocks that you can see here, the purples and the green ones are fermions, which are particles with half-integer spin that we can think of them as material particles. And these particles that we have here are bosons, which are particles with integer spin. These bosons that we have here can be understood as mediator particles. It means that these are the particles, according to the standard model, that are the mediator of the interactions, okay? And this is the Higgs particle, which is a scalar boson. So these 2 theories has been used to describe different phenomena of the universe that we live in, and they have been also used to predict important phenomena of the universe that we live in. Of course, both theories have certain limitations or holes that have to be filled. In the understanding of the universe, how the history of physics teaches that unification of concepts, it is an important thing to take care about in the understanding of universe. For example, the electromagnetic interaction, once upon a time, it was thought to be 2 different interactions, electric and magnetic, and they were unified in the electromagnetic interaction. Afterwards, the electromagnetic interaction was unified with the weak interaction to construct what we call the electroweak theory. And the electroweak theory was unified with the strong interaction to form what we call the standard model of particles. Therefore, it is natural at least to consider the possibility that there exists only one theory that should be able to describe these 4 interactions at the same time, right? But the first theory, the first interaction is described by a geometric theory, and the other 3 are described by a quantum field theory. So in order to have only one theory, we're supposed to be able to geometrize the gauge interactions or quantize the gravitational interaction, okay? There have been recent improvement in this last approach, in the quantization of the gravity. And the community has done this by considering that these particles that are the most elementary particles that conform the matter are not point particles, but extended objects, all right? So what we mean is that instead of a point particle moving on the space-time, with a corresponding word line, we may consider extended objects. These are like an example, an extended object of one dimension, supposed to be a string. And when it moves across the space-time, it defines what we call a worksheet, which is a two-dimensional manifold. And we may consider extended objects of more than one dimension. In the case of 2 dimensions, we will call it membrane. And in the case of more than 2 dimensions, we will just call it brane, all right? And these branes swap what we call a work volume on the space-time. So by considering this, we are able to give a consistent description, a consistent quantum description of gravity. Therefore, string theory is a candidate for a theory of everything, in the sense that it may unify the 4 known interactions. However, in the mid of the 90s, there were 5 different known string theories in 10 dimensions. These are type 2b, type 2a, both heterotic, and type 1 string theory. Okay, so people say, okay, we have 5 different theories, but in the second revolution of superstring, the community found out that these 5 theories were not independent. They were related by a web of dualities. In particular, we have T-duality and S-duality that relate these string theories between them, and therefore this led the community to think that they may be understood as different limits of an only one theory that lives in 11 dimensions, which we call M theory, okay? And dualities of a string theory should be manifested as symmetries of M theory. T-duality is a symmetry that relates theory with different geometry, with a different geometry of the space-time, and S-duality, it is called a strong weak duality because it relates theories in different couplings, in weak and strong coupling. Some important thing to mention, it is that M theory, it is a theory in 11 dimensions, but when it is compactified in a circle, it can be understood as dual to type 2a string theory, okay? And type 2a string theory on a circle, it is T-dual to type 2b string theory on a circle. Therefore, it looks like M theory on a torus supposed to be able to reproduce type 2b string theory, okay? However, the non-perturbative description of type 2b string theory can be understood in terms of another theory that we will call F theory, that lives in 11 dimensions, that offer us a very beautiful relation between physics and mathematics, okay? Therefore, the only thing that I want all you to remind for the end of the talk, it is that in general, for dimensions smaller than 10, for example, compactifications of type 2b string theory can be reproduced from F theory on an elliptic vibration or from M theory at the same time, okay? However, all these theories of quantum gravity is supposed to be able to describe the universe where we live on, okay? And we live on a universe with 4 dimensions and where the energies are smaller, and we use what we call effective field theories to describe theories at the range of energies of the universe that we live in. All the effective theories that may be obtained from string theory, they are said to belong to the landscape, okay? We don't know criteria so far to determine which theory within the landscape is related to the universe that we live in, okay? So far, what we know it is that there is a boundary which is set up by the Swampland constraints, which are conjectures that have not been proven so far. And if you are within this boundary, you are in an effective theory that can be obtained from a quantum gravity consistent theory. However, there are effective field theories that live outside the landscape, and we will call them to belong to the swampland, which are all those effective field theories that cannot be obtained from a consistent quantum gravity theory. So some physicists are now trying to identify if we belong to the swampland or to the landscape. However, the reproduction of the landscape have been done so far from string theory, F theory, or M theory. But M theory, the difference that have M theory with these two cases is that we don't have a quantum consistent description of M theory, okay? So this, therefore, there are some limitations trying to obtain the restrictions that there are on the landscape when you work with M theory. In our work, what we want to do is we have done some improvements in the identifications of some sectors of M theory that they have a well-defined quantum consistent description. And therefore, in this talk, we will try to identify which objects or sectors of our string theory are related to the well-behaved sectors of M theory with a consistent quantum description. And in the midterm or long term, we would like to know if which kind of restriction these well-behaved sectors impose on the landscape of a string theory. Okay, so yes, M theory, it is a theory, as I said before, that lives in 11 dimensions, and it describes some objects has the M2 brane and the M5 branes. The M2 branes, it is a membrane that it is evolving in an 11-dimensional space. The general, the action for a M2 brane evolving on a general background was given by Berkshire-Seskin-1000, and it is this action that we have here. These two terms can be understood as kinetic terms, while this term, it is a Wess-Sumino terms that take into account the coupling with the supergravity 3 form, okay? I and J are index of the work volume of the M2 brane. These are the index of the target space. These are the index of the superspace, which have the tangent superspace, which has bosonic and fermionic index. We have the space 1 forms written in terms of the superspace coordinates, which has the bosonics and the fermionic ones. And the fermionics in this case are Majorana fermions of 11 dimensions. And this pi that we have here, it is the pullback of the superfieldbine to the work volume of the M2 brane. Okay, the superfieldbine is this one, and this is the pullback. In the case of the flat superspace, there is some restriction that come from supergravity in 11 dimensions, and it can be checked that the pullback, the components of the pullback of the superfieldbine can be written in this case like these two equations that we have here, two expressions that we have here, and the bosonic and fermionic components of the 3 forms can be written in this way, such that the action of an M2 brane evolving on a flat superspace can be written as this expression that we have here on the low part of the slide. That means all this information, I put it here, and it can translate in this expression that we have here. So if I consider the imposition of the light cone coordinates and the light cone gauge on the previous action, and I perform what it is called like a Legendre transformation, it can be proved that I can reproduce what it is called the light cone gauge Hamiltonian density of an M2 brane on a flat superspace, which is this expression that we have here. This is the kinetic term of the Hamiltonian, this is the bosonic potential, and this is the fermionic potential, okay? A and B are now transverse index that runs from 1 to 9, and U and V are the index related to the spatial directions of the work volume, okay? These brackets are Lie brackets, which in this context can be understood as symplectic brackets. And this Hamiltonian, it is subject to a constraint, which it is related to the area preserving diffeomorphism. It was shown that this Hamiltonian, it has a regularized model that it is characterized by a continuous spectra, okay? Therefore, for this reason, the community abandoned the idea of thinking the M2 brane has a fundamental object that it is describing microscopical degrees of freedom of M theory, okay? The toroidal compactification of the theory in general does not change the spectral behavior, okay? So when I try to compactify, the spectra remains continuous, therefore another reason for the community to abandon the idea of work with M2 brain as a fundamental object of M theory. However, on the 90s, there was a sector that was found that it has a good properties, all right? This expression that we have here, it only expressed the map of the work volume onto the torus of the target space. I am considering a target space with two directions toroidally compactified, but I can impose where I have what it is called a winding matrix, but we can impose an extra condition, which is called central charge condition, that it's this expression that we have here that ensures that the determinant of the winding matrix, it is non-zero, all right? In the case that this condition it is imposed, the theory acquires nice properties, have the discrete supersymmetric spectrum of the regularized model. Therefore, the M2 brain with this central charge condition may be understood as it is an object that it is describing microscopical degrees of freedom of at least a sector of M theory, okay? The name of this condition, it is because it is a term that appears has a central charge term in the superalgebra of the theory. It can be checked that it implies the existence of a U1 principal bundle over the work volume of the supermembrane, the M2 brain. And it can be checked that this condition generalizes the Dirac monopole condition over Riemann surface of arbitrary genus, okay? The Hamiltonian of the M2 brain with central charges can be written in this way that we have here, where we have the kinetic terms, we have the bosonic potential related to the non-compact directions, we have a symplectic curvature that it is written in this way that we have here, in terms of the covariant derivative, that it is this expression that we have here. We have a symplectic derivative that it is written in terms of the covariant derivative in this way. We have the central charge term, and we have the fermionic terms. Here, it can be checked that the central charge condition ensures that the maps onto the compact sector can be separated by the Hodge decomposition in the harmonic and the exact part of the map. And the central charge condition ensures that the harmonic sector is non-degenerate, all right? So this A, it is just mentioning that we are referring to the exact sector of the compact map. The constraints are the same constraint than before that can be written in this way, and we have a global constraint that it's also related to area preserving diffeomorphism connected to the identity in this case. However, we notice that we can consider, in another case, we can consider an M2 brain with 2 dimensions toroidally compactified, but we can consider a well-defined 2 form written in terms of the coordinates of the torus of the target space. And we may consider a flux condition on this well-defined 2 form. And this 2 form, it is related to the plus-minus components of the supergravity 3 form. So if we do this and we identify the coordinates of the torus with the embedding map of the M2 brain on the target space, it can be checked that these target space fluxes implies the work volume fluxes, which are characterized of the central charge sector. All right, so what we have found it is that non-trivial fluxes on T2 implies the central charge condition, okay? Therefore, we have identified other sectors of M2 brains on a torus, which also share the good quantum properties of the M2 brain with central charge. These sectors were known as M2 brain with C plus minus fluxes, and it admitted 2 different formulations that are connected through canonical transformations, okay? In the more general case, the Hamiltonian can be written in this way that we have here, where the black terms are just the same terms that I showed you before related to the M2 brain with central charge. In the case that I consider the M2 brain with C plus minus fluxes, the only difference will be this term that we have here, that it is a constant term that it is relevant when we have compact directions, as in this case. And if I consider the CM2 brane with fluxes, the only difference will be these two terms that we have here on the inside the kinetic terms, okay? These three Hamiltonians are connected within them by canonical transformation, and the only difference on the spectra and on the Hamiltonian will be a constant shift in the most general case. So this we have identified other sectors of M2 brane on a torus that has a good quantum behavior, has a discreteness of the supersymmetric spectra. These sectors are characterized by some non-trivial symmetries, as for example, we have some non-trivial U1 gauge symmetries. This is a well-defined two form that define a flux condition on the work volume. We have another two form that can be understood have the field strength of a gauge field, which is topologically trivial but contains information of the dynamical degrees of freedom of the theory. And we have another well-defined two form that it resides on the same principal bundle as the previous one, but it contains information about the dynamical degrees of freedom of the theories, okay? The three connections are this connection that we have here. And there is also a symplectic gauge symmetry, which is topologically trivial, but it has non-trivial repercussions on the theory. And I want to emphasize that this curvature, it has the same form as the U1 curvature, which is topologically trivial that I showed you before, okay? So these are the non-trivial symmetries of the theory, and the global picture, it was given in terms of symplectic torus bundles with monodromy containing SL2Z, where we have considered a foliation of the work volume in such a way that the special direction form a Riemann surface of genus 1, which is this sigma that we have here, that it is the base manifold of the symplectic torus bundle. The fiber is the target space, but the non-trivial information will be contained on the compact sector. The structure group are symplectomorphism of the torus, and the monodromy, it is contained in SL2Z. The inequivalent classes of symplectic torus bundle are classified in terms of the coinvariants, which are given by this expression that we have here, where Q and W are the charges of Kaluza-Klein and winding respectively, okay? And this is the monodromy subgroup. It can be checked that when the monodromy is trivial, the coinvariants only have only one element, okay? For non-trivial monodromies, we have like as kind of equivalent classes of fiber bundles. Moreover, the central charge condition implies the existence of a U1 principal bundle, which is non-trivial on the work volume of the theory. And it can be seen that this is related to the connection that I showed you in the previous slide, that it is written in terms of the harmonic sector of the embedding map to the compact sector, okay? Therefore, the picture of this M2 brane can be seen like this. This is the torus of the work volume, this is the torus of the target space, and this is the U1 principal bundle related to the flux condition, or equivalently to the central charge condition. One question, it is that we ask ourselves, it is what is the relation between these two fibers? We have a torus that it is related with the symplectic structure of the fiber bundle, and we have a U1 principal bundle. What is the relation between these two fibers that we have here? And we have found that this global picture can be understood in terms of a twisted torus bundle, which is a twisted torus fiber over the base manifold with a monodromy contained in SL2Z, okay? As before, inequivalent classes of twisted torus bundle are given in terms of, are classified by the coinvariance of the fiber and the base manifold. The consistence of the twisted torus bundle can be checked in terms of the well-defined flux condition on this curvature, okay, that it is the field strength of the connection that have information of the minimal connection, which is non-trivial, and the topologically trivial connection, but the one that has information about the dynamical degrees of freedom of the theory, okay? Other way to check the consistency of this fiber bundle, it is by the fact that the symplectic curvature, it has the same expression than the topologically trivial curvature. This description allows to reproduce the 11-dimensional origin of gauge supergravities in 9 dimensions, okay, which was not known until the date. Okay, so now I want to, what I just said before, it is try to identify some sectors of M2 brane theory which has a good quantum behavior, and therefore they can describe microscopical degrees of freedom of M theory. Okay, so therefore we don't know a quantum description of M theory, but we know a consistent quantum description of some sectors of M theory. Therefore, we would like to know which objects of a string theory are related with these non-trivial sectors, okay? And we did this in 2 different ways. The first way was to consider the dimensional reduction plus the scalar vector dualization of these non-trivial sectors of M2 branes, and we found that by this process we were able to reproduce type 2A D2 branes compactify on a torus with some kind of non-trivial flux conditions on the work volume, and with some non-trivial gauge symmetries which are inherited from the 11-dimensional picture. Another way that we try to obtain information of string theory from these sectors was by the double-dimensional reduction of these theories, and we were able to reproduce type 2B PQ string compactify on a circle, including a case where the symmetry group is not SL2Z, but it is restricted to the abelian subgroup of SL2Z, okay? I will mention now both approaches, but I will try to focus on the second one, which is the name of the talk. Okay, type 2A D2 branes with quantized Ramon-Ramon and Nevesoir background fields. This dualization process, it is very known in the literature, and we know that M2 brane on compactify on a circle, if you follow this dualization, you are able to reproduce what it is called a D2 brane on 10 dimensions, okay? This dualization process, it commutes with the Lightcon gauge, okay? That means that I can start from a covariant Lagrangian, perform the dualization, and then fix the Lightcon gauge, and this is equivalent that from the same Lagrangian, fix the Lightcon gauge, and then perform the dualization. I will obtain the same Hamiltonian, which in this case is related to a standard D2 brane, okay? However, we are not interested in standard D2 branes or standard M2 branes. We are interested in non-trivial sectors of M2 brane. I showed you before that the most general Hamiltonian can be written in this way that we have here. And I just want to mention that if I follow the process of dualization, I obtain this Hamiltonian that we have here, which has some terms that are similar to a standard D2 brane Hamiltonian, but it has different terms, pardon, that are related to this non-trivial sector. For example, we can see this kind of Maxwell term that can be written in terms of the minimal curvature and the topological trivial curvature, which are inherit from M2 brane, and the same with this symplectic curvature term that we have here, okay? This curvature that we have here, it is a curvature that it is characterized of D2 branes, but in this case, due to the flux condition, it appears with a non-trivial aspect, okay? This Hamiltonian, it is subject to this constraint that we have here. The first one, it is the standard Gauss constraint, which is related to a U1 symmetry that it is characterized of D2 branes, and these 2 other constraints are related to area preserving diffeomorphism, which in 2 dimensions are symplectomorphism connected to the identity. And the flux conditions that we have on the theory on 11 dimensions implies some quantization conditions on the plus minus components of the Ramon-Ramon 3 form, which is a well-defined 2 form on the work volume. and on the plus component of the Neveswar background field, which is also known as the B field. A good thing to see it is that in this case, we have that the Neveswar-2 forms can be understood as it defines a closed to form on the world volume, and it can be understood as a field strength of a non-trivial U1 connection. This is non-trivial in the sense that normally the Neveswar-2 form, it is not the field strength of a well-defined connection, but in this particular case, due to the flux condition, it happened that it is a well-defined field strength related to a non-trivial U1 connection. The non-trivial symmetries of these D2 branes are these symmetries that we have here. The first one, it is a standard of normal D2 branes. This symmetry, it may be non-trivial, but in our case, we are considering topologically trivial, and it has the same symmetries that has the non-trivial M2 branes, but in this case, the D2 branes inherit these symmetries, and these are not were not known in the context of the branes. Okay. Moreover, we have also a symplectic gauge symmetry, which is inherit from the non-trivial M2 brane, and the fact that the symplectic curvature, it has the same structure than the topologically trivial curvature, which contains information about the dynamical degrees of freedom of the theory, lead us to think the possibility to describe globally these non-trivial D2 branes has twisted torus bundle with an extra U1 principal bundle related to the Dirac-Born-Infeld symmetry. Okay. The Hamiltonian, in the most general case, can be written in this way that we have here, as I showed you before. The black terms are standard terms of a normal D2 branes, okay? But in this case, if I start not with a normal M2 brane, but with an M2 brane with central charges, which has a good quantum behavior, I have that I can obtain these two terms which are new in the context of the branes, okay? If I start with the M2 brane with C plus minus fluxes, I am able to reproduce not only the red terms, but also these blue terms, which were also not known in the context of the two branes. And if I start with the most general case, which is the CM2 brane with C plus minus fluxes, I am able to reproduce this complete Hamiltonian, okay? So if these are not D2 branes, what are they? We show that we were able to reproduce this Hamiltonian starting from 11 dimensions, but we also start from a standard D2 brane Hamiltonian in 10 dimensions, and we compactify 2 dimensions on a torus, and we ask ourselves which kind of condition shall we impose on this Hamiltonian in order to reproduce these Hamiltonians that were obtained from non-trivial sectors of M theory. And the answer, it is that the black terms are standard terms of a D2 brane on a torus, but in order to reproduce the red term, we should consider a standard D2 brane with Ramon C minus fluxes. The blue terms can be reproduced if we consider Ramon and Neveswar quantization conditions, and the full Hamiltonian can be obtained if we consider Ramon and Neveswar to form fluxes on the world volume. Okay. So we have obtained this Hamiltonian started from M theory and also starting from the Dirac-Born-Infeld description of the branes in 10 dimensions. So if these are not standard D2 branes, what are these objects? The possibility to understand this subject as bound state of fundamental strings and DP branes remains as an open question, okay? And the description of these sectors can be also given in terms of twisted torus bundle with monodromy containing SL2Z, okay? All right, so we so far have identified some objects of type 2A string theory, which are related to non-trivial sectors of M2 brane, and this can be useful because the branes has been used to construct models that are trying to reproduce the phenomena that we see in the universe. So a work that we can do is try to see our D2 branes, which kind of phenomenological information can be obtained from these non-trivial d-branes, okay? Now I will talk about type 2b bound state of PQ3 on a circle that are related to non-trivial sectors of M2 brane. It was mentioned by Schwarz in this work that type 2b supergravity contains an SL2R symmetry. That means that the action of type 2b supergravity can be written in such a way that it has an SL2R invariance on the action. This led Schwarz to conjecture the existence of what he called PQ strings, which are strings that has not only Ramon-Ramon charges, but also Nevessuar-Nevessuar charges. I mean, not only Nevessuar-Nevessuar charges, but also Ramon-Ramon charges. So PQ string are strings that has both Ramon-Ramon and Nevessuar-Nevessuar charges, and it was interpreted by Witten as bound state of fundamental strings and D1 branes, okay? Because fundamental strings are characterized by a Nevessuar-Nevessuar charge, and D1 branes are characterized by Ramon-Ramon charges. Therefore, this PQ string, according to Witten, can be understood as a bound state of fundamental strings and D1 brane. The mass operator of a PQ string on a circle, it is given by this expression that we have here, where we have the Kaluza-Klein term, we have the winding term, and we have the oscillators. And the tension of a PQ string, it is given by this expression that we have here, where lambda 0, it is the axiodilaton, which is a complex scalar field formed by the Ramon-Ramon 0 form and the coupling constant of the string, okay? But as I showed you before on the first slide, type 2b and type 2a are T-dual within each other, and type 2a string theory may be understood as M theory on a circle. Therefore, M theory or at low energies supergravity in 11 dimensions on a torus should be able to reproduce type 2b string theory on a torus, type 2b supergravity on a circle. This led Schwarz to try to reproduce this mass operator from what he called an M2 brane wrap n times on a torus, okay? And he, in a heuristic way, he proposed that the M2 brane wrap n times on a torus supposed to have a winding term, that it has this expression that we have here, and it's supposed to have a Kaluza-Klein term that can be written in this way that we have here. And he mentioned that there's supposed to be another terms here that he was not able to compute in the 90s, okay? And what he says, it is that if you consider this mass operator and you relate it with the mass operators of the string in this way that we have here, where lambda 0, that it is the axiodilaton that I tell you before, you identify it with the Teichmuller parameter of the torus, and you write beta square in terms of the tension of the M2 brane, the tension of the string, and the area of the torus, and you wrote the radius of the type 2b theory in terms of the 11-dimensional information, he proved that you are able to reproduce the Kaluza-Klein and the winding term from this expression that we have here, okay? He was not able to reproduce the oscillators because he was not able to compute these terms that were here. He just mentioned that these terms are related to the membrane excitations that he don't know how to compute, okay? However, we know that the mass operator of the M2 brane with C plus minus fluxes, in the case that we have a trivial monodromy, can be written in this way that we have here. And if you notice, these are the winding term and the Kaluza-Klein terms that Schwarz wrote in his paper. So the case that Schwarz considered, it is the non-trivial M2 branes that we are working so far. But we are able to know which are the membrane excitations that Schwarz doesn't knew how to compute, okay? And these membrane excitations are related to the Hamiltonian of the non-zero modes of the supermembrane, which are the information risk. I mean, you have the normal Hamiltonian and you take out the information of the center of mass and you stay what it with what it left. Okay, so these are the non-zero modes of the Hamiltonian. And it can be written in this way that we have here, where the prime, it's just to remind that we have take out the zero modes of the Hamiltonian, and as you can see, the central charge term, it is not written in this Hamiltonian because it was used to reproduce the winding term on the mass operator, okay? So, as we were able to reproduce the winding and KK term of Schwarz, but we also know how to compute the membrane excitations, we ask ourselves what can we do in order to generalize the work done by Schwarz to the supersymmetric degrees of freedom, considering the membrane excitations. And what we have found, it is that if you consider a double dimensional reduction, we were able to obtain this Hamiltonian that we have here, where we have a kinetic term that it's really, it has the same form that a string Hamiltonian, like Light-on-gauge Hamiltonian. We have a bosonic potential that it has also the same form that a string Hamiltonian, and we have a kinetic term that it also has the same form than a string Hamiltonian. Here chi, it is a coordinate that has dimensions of length, and it is written in terms of x8, which is one of the directions of the target space, plus some SL2Z transformations that we have previously done using the symmetries of M2 brane on a torus. So far we were able to show that the non-zero Hamiltonian of the M2 brane with fluxes can be written in this way that we have here, which is really reminiscent of a string Light-on-gauge Hamiltonian. Therefore, if we follow the standard procedure, we are able to reproduce the full mass operator of the M2 brane on the string configurations, which has a winding term, a Kaluza-Klein term, and some term related to the oscillators that it come from the membrane excitations, okay? I forgot to say that here lambda are SO7 spinors. In this process, we had to write the Majorana spinors of 11 dimensions in terms of SO7 spinors, okay? Therefore, if we follow the procedure proposed by Schwarz, we are able to reproduce the full mass operator of a PQ string on a circle, including the oscillator terms, and we also done this work considering supersymmetric degrees of freedom that were not considered by Schwarz at first instance, okay? The tension, as I showed you before, it is this one. The axiodilaton of the theory was identified with the Teichmüller parameter of the torus, and beta square and the radius of the type 2B theory square are written by the same expressions that I showed you before. And I would like to stress that the global constraint related to the area preserving diffeomorphism connected to the identity on the supermembrane was able to reproduce on the string configuration the level matching constraint that it has exactly the same form of a string theory compactified on a circle, okay? Here N it is the winding term and M it is the Kaluza-Klein term. If we consider the term of the C plus fluxes, the only difference will be a constant term that can be written in this way in terms of the tension of the string and the radius and an integer related to the flux condition, okay? So we were able to reproduce to obtain the supersymmetric PQ string on a circle from non-trivial sectors of M2 brane by generalizing the work done by Schwarz. However, let us remind that we have started with an M2 brane with trivial monodromy. That means that the coinvariant only contain one element, okay? So we ask ourselves what happens if we consider a non-trivial monodromy, and in that case, the coinvariant will not have only one element, but there will be a sort of equivalent classes of Kaluza-Klein charges, okay? So in order to do this, let us go back a little bit to M2 brane, and let us mention that M2 brane with fluxes has two main symmetries. These are an SL2Z symmetry that it is called SU duality, that it acts on the torus of the target space, and it is a symmetry of the supersymmetric Hamiltonian. and we have an SL2Z symmetry related to the work volume of the theory, okay? It can be checked that symplectomorphism on the torus are in one-to-one correspondence with symplectomorphism on the base manifold, okay? What I want to stress here is that the Kaluza-Klein charges transform in an orbit of charges generated by the monodromy, okay? Because G, it is an element of the monodromy subgroup. Therefore, the theory, the global theory, it is classified by the coinvariants, but the local theory, it is only well-defined, not in the coinvariant, but in an orbit of charges generated by the monodromy, which is contained in the coinvariant of the fiber, okay? Therefore, we ask ourselves, where can we formulate the theory in such a way that it is formulated not only in the orbit, but on the coinvariant of the fiber in such a way that we have a formulation on the module of coinvariant. And in fact, we found that if SL2Z, well, we know that it's generated by these two matrices, we will restrict ourselves to the parabolic subgroup in this presentation. And in particular, this parabolic matrix contains only trivial information. So we will restrict ourselves to these kind of matrices that we have here, or the one that are generated by this matrix that we have here. And in this case, we found the next thing. The mass operator of an M2 brane with fluxes and monodromy in general can be written in this way that we have here, where we have the winding term, Kaluza-Klein term, and the membrane excitations that, as I showed you before, it is related to the non-zero modes of the Hamiltonian. But we have found that this, in the case of the parabolic monodromy, this mass operator contains a new symmetry, which is an SL2Q symmetry, okay, that acts on the Kaluza-Klein charges, on the winding matrix, and on the Teichmuller parameter in this way that we have here, where lambda, it is an SL2Q matrix, okay? And lambda star, it is a matrix that it is defined on the, it acts on the base manifold on the theory. The particularity that has this new transformation, it is that it can be checked that it maps arbitrary charge on the coinvariant of the charge, which for the parabolic monodromy are only characterized by an integer q, that it is this q that we have here. So in equivalent classes in equivalent coinvariant classes are given by different q's, okay? So this transformation maps q onto the coinvariant, okay? Moreover, we have found a transformation between different parabolic coinvariants, which are, as I showed you before, are classified only by the integer q, okay? And in this case, its transformation, it is also given by a parabolic matrix. So by doing this, we can say that we have the theory formulated in terms of a particular charge, but we have a symmetry, which is a symmetry of the Hamiltonian, that it can map this particular charge to the full coinvariant. Therefore, we can say that we have found a formulation of the theory in terms of the parabolic coinvariance. Therefore, if we reproduce what we have done before, we were able to obtain what we call a parabolic PQ string, which contains a mass operator that is given by this expression that we have here, where the tension, it is proportional to the tension of the PQ string, okay? And the main difference that this has with before it is that the symmetry group, it is not SL2Z, has the standard PQ string, but it is restricted to the parabolic subgroup of SL2Z, okay? Therefore, M2 brane with C minus fluxes and parabolic monodromy, it is able to reproduce type 2B parabolic PQ string whose low energy limit, it is related with type 2B parabolic gauge supergravity. This parabolic PQ string was was obtained by consider a compactification on a twisted torus of F theory. F theory, it is a theory that I mentioned at the beginning of the talk that can be understood as a non-perturbative limit of type 2B. And it is a compactification on a twisted torus of F theory. In this case, we are not compactifying on a twisted torus, but as I showed you before, we have identified a twisted torus structure within the formulation of non-trivial M2 branes, okay? Therefore, we were able to obtain this parabolic PQ string from these non-trivial sectors of M2 branes, which are well behaved from a quantum point of view. Moreover, the symmetries that we have identified in the context of M2 brane should be manifested at the level of a string theory in this way that we have here. Therefore, that means that we have a certain kind of PQ strings, of parabolic PQ strings, which has an origin on the same fiber bundle on 11 dimensions with the same Hamiltonian. Because when we formulate the theory in terms of the coinvariant, we have generalized the orbit of charges where it was locally described in the past, and we can say that there are certain PQ strings that have their origin on the same fiber bundle with the same Hamiltonian, and moreover, we can identify some transformation between parabolic PQ string, and there is also a duality between inequivalent PQ string, okay? Because we found a transformation. The transformation between coinvariants at the level of M theory can be understood in 10 dimensions as a duality between inequivalent PQ string. Therefore, in order to conclude, we have found that there are at least two dual sectors of M2 brane on a torus with discrete supersymmetric spectrum. These are M2 brane with central charge and M2 brane with C plus minus fluxes, or equivalently CM2 brane with C plus minus fluxes. The global description of these equivalent sectors is given in terms of twisted torus bundle with monodromy in SL2Z. They are characterized by world volume fluxes and non-trivial gauge symmetries, which are U1 and symplectic, induced by the area-preserving diffeomorphism. The orbit of charges where this theory were originally formulated is extended to the inequivalent classes of coinvariants for parabolic monodromies. The dual theory on 10 dimensions corresponds to type 2A D2 branes with quantized Ramon-Ramon and Nevesoir background fields, which manifest as two-form world volume fluxes on the theory, area-preserving diffeomorphism, or equivalently symplectomorphism in 2 dimensions on this D2 brane with world volume fluxes produce unnoticed non-trivial U1 gauge symmetries and symplectic symmetries. The global picture is given by twisted torus bundle with an extra U1 bundle structure related to the Dirac-Born-Infeld gauge symmetry. Bound states of type 2B PQ string with SL2Z symmetry are related with non-trivial sectors of M2 brane theory. We found bound state of PQ string with a symmetry restricted by the parabolic subgroup. There are Z inequivalent from the 11-dimensional perspective because we have identified some PQ string with the same Hamiltonian and the same bundle structure, and parabolic PQ string on a circle correspond to the quantum uplift of type 2B parabolic gauge supergravity in 11 dimensions. I would like to end by thanks all these people and projects that it's here, and thank you very much for your attention. And if there are any question, I would like to try to answer it.
So thank you, Camilo, for your talk.
Thank you, Bruno. I am trying to stop to share the screen, but I don't know what. All right.
That's okay. Thanks for everybody who presented today. Tomorrow we'll start at the same hour with another 3 speakers. And then if no one has any questions or comments about either the last talk or the session in general, we can end today. Then thank you everybody for coming. And then tomorrow at the same time, And that's it. Good night, everybody. Thanks for
Thank you.
presence.
Thanks,
Goodbye,
Bruno.
thank you.
Good night.
Bye.